So we have two groups that has successfully do the classification task, and as you might have noticed, it's very easy to upgrade this into an object detection. May I ask, what did you do with yesterday's task? there were a code that has a bug, and you should have been searching all the night for this bug and tell me today about it. Did anyone find the bug? Okay, no problem. It was a long day, and I do not expect that you will be investing your time on this. Now let's go to a new topic. This time it's about unsupervised learning. Okay. So Jeremy, you still in the workshop?
Yeah, sorry.
So CNN MLP was about supervised learning, right? Now we will discuss another kind of algorithm that can learn from unlabeled data. So we will describe a new concept for you, which is called Boltzmann machines. And we have a special case of these machines that's called restricted Boltzmann machines, RBMs, that we will discuss. Afterwards, we will discuss how to build deep belief networks out of these Boltzmann machines. You're still in the workshop, right? Okay. What is Boltzmann machines? Let me firstly tell you about some difference between two kinds of models. We have two kinds of models. We have generative model and we have discriminative models. All what we have discussing so far is the discriminative models. The objective was that we have data. Each data point has an X and Y, has some data and its ground truth or label, and the objective was to find the probability of Y given X. This is the question that we were trying to answer. What is the probability of being a cat given this image? What is the probability of being a dog given this image? What is the probability of being airplane given this image? And at the end, as you have done in the workshop, you select the maximum posterior probability. It's called posterior because there is something that happened already. X is given to you. So it is the probability after the fact that X is given. The discriminative model is trying to answer this question. What is the probability of Y given X? So assuming that we have this data, this is the training data, this is X and this is Y, this is X and this is Y, and we have 4 training samples. A discriminative model can learn from this that the probability that Y equals 0 given X equal 1, given X equal 1, what is the probability that Y equals 0? It's all the time equals 0. So the probability is that Y equals 0 given X equal 1 is 1. And the probability that Y equal 1 given X equals 0 is 0. It didn't happen in the data set. So a discriminative model can figure out these rules. Here we can figure it graphically because it's very simple. But if you have images, tons of images, millions of images, and with ground truths, can you look at the data and figure out those numbers? For sure no. This is why we train a machine learning algorithm to do it. But here it's very simple that we can put some rules that encode our machine learning. If X is equal to, the probability that Y equals 0 is half of the time, and the probability that Y equal 1 is the other half of the time. So if we want to build a generative model out of this data, the generative model is trying to do data representation. It does not need to answer the question, what is the probability of the label given the data, but it tries to answer the question of how much of the time this label is coming with this data. Okay? So it is trying to answer the question of what is the probability of having X and Y. What is the probability in this data to have X equal 1 and Y equal 0? It happens 2 times. right? Out of 4 samples, so the probability that we will have 1, 0 is 2/4, which is 0.5. What is the probability of having x equal 1 and y equal 1? It doesn't happen on all the training data, so the probability of it is 0. What is the probability of 2 and 0? It happens once out of 4 times in the training data set, so it is a quarter. And what is the probability of having 2 and 1? It is a quarter. Sorry for announcing the start without being here, but we were discussing that we have 2 different types of models, the discriminative model and the generative model. If you have this kind of data, training data, the discriminative model, which we have been describing all the time yesterday and today, it tries to find what is the probability of the label given some data. So what is the if I ask you, given this data, if x is 1, what is the probability that y equal 0? If x is 1, okay, so x is 1, happens here and happens here. What is the probability that y equals 0? 100. It happens all the time. Because if I know that x equal 1, I'm not looking into this. It is a posterior probability. X equal 1. I know this for granted. So what is the probability that y equals 0? It's all the time. What is the probability that y equal 1? It is 0. Because it doesn't happen anytime. The generative model is trying to find the probability of x and y. What is the probability of co-occurrence between these 2 values together? So what is the probability of having x with 1 and y with 0? We have 4 possibilities, and this possibility, 1, 0, happens twice. So it's 2 by 4. So it's half. What is the probability of having 2 and 0? It is 1 divided by 4 scenarios. Okay? So now we are speaking about unsupervised learning. And the objective behind unsupervised learning is to try to model this, to create some belief about some intermediate signal in the system. Okay, we do not know the labels, but we will create some belief about some signals that can encode the labels, because we do not know it, and we will try to figure out what the distribution of x looks like. There is an interesting concept called the entropy. I have asked your colleague who was the first to finish the assignment to send me this photo. So we were classifying this image using Inception ResNet version 2, and the output was jet fighter with a probability of towards 80%, and we plotted the probability. Oh, you can't see it. You always don't tell me. Okay, this is the image, and we have plotted the probabilities, the posterior probabilities, over all the possible 1,000 classes. Okay, as we can see here, this class is having 80%. This is the airplane or airjet class, and we have some confusion here, and everywhere else is giving a very low probability. If we compare this with something like this, let's use a blackboard. If we compare this entropy which looks something like this, if we compare it with another entropy that looks like this, which one is better? The first one seems confident, and it seems confident in the right sense, because the answer is correct, which is a good thing. We say that this is a distribution and this is a distribution. We say that this distribution has a low entropy. and this distribution have a high entropy. It's a concept that is inspired by thermodynamics, not computer science, and we borrow this concept here. And this is why we say restricted Boltzmann machines. Did you hear the Boltzmann word before? Is it first time to hear the word Boltzmann? Do you remember where did you hear it? It was in thermodynamics. There were some constant in the equations called K, capital K. It was a Boltzmann constant. And because here we are using entropy and energy, we are borrowing this concept, and this is why it's called Boltzmann machines. Okay? So, we will define some function called E, energy, capital E, energy. And this function will represent the entropy of the distribution of X. We will have a visible layer and a hidden layer. Okay? The visible layer, if we have an image of, let's say, 100 pixels, so we will have 100 neurons. Okay? Each one is taking a pixel. And we will have a hidden layer. And you can choose any number of neurons for your hidden layer. It's like you are designing a CNN and you are choosing any number of neurons you see fit, depending on your design. The purpose behind this hidden layer is to create some representation for the input data. And you have weights connecting both layers, but here the weights are can be bidirectional. You have a weight here and a different weight here. And you have a weight here and a different weight here. Also, you can have weights that connecting neurons at the same layer. We name the weights connecting the visible layer with the hidden layer as W, the weights connecting the visible layer neurons as capital U, the weights connecting the hidden layer together as capital V. And we define the energy function, which is a function of X and H. H is the values of this neuron, and X is the values of these visible neurons. The definition of E is, as you can see here, H here is a vector of 3 in this example. X here is a vector of 2 numbers in this example. And W is a matrix that describes these weights. So when we multiply a horizontal vector called V, it's like the bias, by, so each neuron has a bias. So the B here is 1, the dimensionality of B transpose is 1 by 3. It's a horizontal vector. And H, by default, vectors are standing. If anyone specify, by default, he means that vectors are standing. So H here is a standing vector. The dimensionality of it is 3 by 1 because it contains 3 numbers. If we multiply a horizontal vector containing 3 elements with a vertical element containing 3 elements, so we get a single number, okay, scalar. The same case here, also the same case here, we have 3 numbers, and we have a matrix that is 3 by 2, and we have a standing vector that is 2 by 1, and if we multiply all of these 2 vectors by this matrix, we will obtain also a scalar. The same case goes for this term. The thing that I need to tell you is that for each value for the input and the hidden neurons, you get an energy. And we will define our probability of having these values of X and H as inversely proportional to this energy. This is the graph for exponential minus X over some constant. It goes like this. If X is increasing, the value exponential E minus X over some constant decreases. Okay? So here is the same. We say exponential minus something over some constant. Okay? So if E because here if x is increasing, the value of the expression decreases, which is inspired from this. We defined E as an entropy, representation for the entropy, and hence we say that when the probability of the correct class increases, the entropy decreases. When the probability decreases, the entropy or the energy increases. This is why we selected it in this way, and we could have selected any other formulas that do the inverse relation, but exponential has good characteristics, especially that we will use negative log likelihood function, so the log will cancel the exponential, as you are going to see. So this makes sense, and this is our assumption for the energy. And let's see how this Boltzmann machine will be able to do data representation for us without having any labels. Do you see any Y's here? Y? Any Y? Any ground truths? Any label? No. There is no Y. There is no ground truth. There is no label. We have X. X is the data, and H. H is the internal representation of the data. Okay. Initially it is random, but with time it will adapt to better represent the data, as we are going to see. Okay, very good. So, given any value of x and any value of h, x is 2 numbers, h is 3 numbers, we can find E, and if we know E, we can directly find what is the probability of x and h. Let's look to the system as an overall. If you ask me, if you give me some data and I train this system, what will you be interested in? You will be interested in to tell me what is the probability of x, what is the probability of image. I will give you an example. Do you remember the networks that was composing music? It was innovating things. How can it innovate things? Because it has listened to lots of music, so it formulated some probability distribution called P of music, roughly speaking. And she created its own understanding of music. Initially, that distribution was very high entropy, but with time, with listening to music, it started to shape this distribution to have low entropy. So it started to construct P of x, and it used this, it started to sample from this to innovate. If you have the probability distribution of some variable, you can sample from it, right? To generate music, you just need to sample some music from the probability distribution of music. To sample, let's assume that we will train some network to draw cats. We need a network to draw cats. We provide it with tons of cats, so it understands cats, and it will create the following distributions. Let's assume that we constrain the image to be grayscale 20 by 20. So, what is the probability of x1, the first pixel here? Initially, it knows nothing. The network doesn't know anything. But with seeing cat images time and time again, it starts to know that to draw a cat, all of the images of cats have some characteristics for this pixel. So it starts to create its own belief about this pixel. And also for the second pixel, B of x2. We name all of this as one distribution, which is B of x. So the network, once trained, starts to understand how to draw a cat. What is the distribution of drawing a cat? And once you ask it to draw a cat for you, what it will do? Okay, what is the probability of giving x1 with this? So the network now want to draw a cat for you. So it will draw it pixel by pixel. Now the network want to know which value it will put in this pixel. So it will consult this distribution, its knowledge, and it will try to sample from it. Okay? You can say, okay, the probability of giving x1 should be highest here, so the pixel should be this pixel, right? And for the second pixel, please pick up this pixel, assuming this is 140, valid, and this is 20. So I will put at this pixel a value of 144, and at the second pixel, I will put 200. And it will do the same process with all the 400 pixels, and eventually you have the image of the cat. And if you tomorrow ask the network to draw another cat, it will draw the same cat, because you constrain it to always pick up the highest probability for each pixel, which is not good. You should sample naturally from each distribution. Meaning that if you do sample from bx1 1 million times, so that assuming this is 0.5 and this is 0.3, so 0.5 of the 1 million time you will pick up this pixel, and 30% of the 1 million times you sample you will pick up this pixel, and as much large as the number of samples you obtain, as much valid what I'm saying now is. Okay. So questions until now? Clear? Okay. So now we can create a network that can look to cat images and draw cat for us. But the question is how the network will learn this distribution from the images. And this is what is done using the Boltzmann machines. It will create its internal representation about the data, okay? And it will use it to tell you what you want. What do you want? You want B of X, but it has provided you with a means that you can calculate B of X and H. What's H? If you are looking to the system from outside, I don't know what's H. I'm asking you what is the probability that X equal this image. X here is an image, because X1 is a pixel, X2 is a pixel, but X as a vector or a matrix is an image. In general, it is a combination of all of these distributions. So we need to ask the network what is the probability of giving this image as a cat. We are interested to know B of X, not B of X and H, but it provides you with B of X and H. So what to do? Total probability. Total probability. So you can say, okay, what is the probability of X? It is the probability of X and H equal million plus B of, here it should be integration. So B of X is the integration of B of X and H over dH for all values of H, right? Okay, so let's simplify things. We will constrain H to be a binary, okay? So this is now a summation from I equals 0 to 1, right? B of X, Y, I, or H equal I, right? So given B of X and H, you can get B of X for anything you want. Let's have a numerical example so you digest this. You have a question? Okay. We have some data, and we trained already a Boltzmann machine to understand this data. How? We do not know, but we have data, and we trained as a Boltzmann machine to understand that data. And once it is trained, we find out these are the weights. The knowledge is still in the weights. It's a normal neural network. So if you want from this to calculate the probability of X equal 0, 0. X is two-dimensional feature vector. So if you want to calculate B of X equals 0, 0, will you be able to calculate it from the network? Yes. This is how we calculate it. So we define all the values of, let's assume we want to calculate B of X equals 0. We will do so. X x can be 0, 0, while h can be 1, 1. And also x can be 0, 0, but h is 1, 0. So we write down all the possible combinations for the h vector. And for each combination, we can calculate minus e, because minus e or e is a function of the network. It just requires from you x and h. Given x and h, given x and h, you can calculate e. Once you have e, you have b. So, given this x and this h, we will calculate e. It's very simple, you can verify it's mathematics. And from minus e or e, we will calculate b of x and h. B of x and h. And, he calculates it in 2 steps. He first calculates e, and then e to the power minus e, and from this he calculates b. So we calculate e, then b. And we calculate b of this x and this h, it is this. And we calculate b of this x and this h, it is this. And we calculate b of x and this h, it is this number. And we know that what is the probability of x equals 0, 0? It is the summation of all of this. Okay? So, given a network, we can get any b of x. So now we understand that this network is encoding the distribution. Because if I give to you this network, it's trained, this is the weight, you have the distribution of x, right? Because if I give this network to you and ask you, what is the probability that x equal 1, 1, 1, 0, 0, 0? You can do these derivations, given that you have these weights, and tell me the probability is like this. So you have this distribution, okay? You can query it with any value for x and get the answer. We are speaking about 2 inputs only. This is trivial. Usually you have an image here. So you have 24 by 24 by 3 numbers here, okay? Yes. Usually also people treat x as a binary as well to simplify things. So it's 24 by 24 only grayscale image. Yes, please.
So here in the Boltzmann machine, there are the hidden layers which are providing us this probability. Why in a regular network we couldn't add another input which could, for example, represent a hidden layer? Why we need? Why we have to have the Boltzmann machine to have the distribution over all the x variables?
Okay, so let's get back to the concept. What we have been discussing, CNN, for example, cannot tell you what is the probability of x. It cannot tell you like this. It tells you what is the probability of y given x. You give an image and you ask it for the possible label, right? Now we need, can you have a CNN and you ask it to draw something for you? No. You can ask it, you can give it an image, and you ask it for p of y given that image, given that x. But can you ask it what is the probability of this image? Can you give it the airplane you have got and ask it what is the probability of it? What is the meaning of this for a CNN? But in unsupervised learning, here RBM is just an example. You can ask it what is the probability of this airplane. What is the meaning of this question? If you have this trained RBM and you give it an image and you ask it what is the probability of this image, the question seems not complete. The meaning of this question is that how much probable is this image compared to what you have seen during the training? Is it something similar to what you have seen, or is it outlier? Okay, this is the probability of x. So we are trying to create representation for the data set. Okay?
Yes, this is right. If you go back to the previous slide, maybe you already mentioned that, but what is z in the probability?
Sorry. Okay. Now we say that the probability needs to be inversely proportional with e. So that was enough. We could say p equal exponential minus e. This is an inverse relationship as we have seen, and we calculated E. We decided to use E because that we will use log. What is Z? Z is because that we are saying this is a probability distribution, and the addition of all of this does not guarantee to be 1. So we divide by Z. What is Z? Z is the summation for the numerator E to the power minus E for given X and H. It's an integration or summation if they are binary for H equals 0 to 1 and X equal 0 to 1. Okay? Usually X is a very big vector, and maybe not necessarily it is binary. This is why we call this term it's intractable. You cannot calculate it. Okay? But as you will see from here on, we do not need to calculate it. Okay? I dropped it. I should have said it. I dropped it.
And just a second quick question. So regarding Boltzmann's machines, unsupervised learning, and it learns a probability distribution of the inputs.
Yes.
That means it's based on the data that we provided. So if we want to get to learn a probability distribution for cats, for example, images of cats, that means it's our job to provide it a data set with only cats.
Yes.
If we provide a dog in the middle, it will just confuse the system. The system will have no.
No, you will not confuse it. You are posing it a different problem where he should understand that life is composed of two things, and this is the representation of these two things. And when you give it an image of dog, it will give a high probability for it. If you give it an image of cat, it will give a high probability for it, but it doesn't discriminate between them.
Yeah. So you'll actually be training it on another problem than the one you initially intended.
Exactly.
So you define the problem you want to solve based on the data you input.
Exactly. So you give it the data, he will represent this data and create his own belief about it. If you wanted to use this belief for a classification task later on, it will be very useful as we are going to see. Okay? But now you have a model that represents the data very well. Why it represents the data very well? Because as you are going to see, we are trying to minimizing the entropy. This is the criteria we have chosen. Okay? Okay. So given a restricted, given a Boltzmann machine, we can have a distribution over the training samples. It is the simultaneous probability of X given A and of A given X, expressed as the shared weights between the two layers of the RBM. So the probability is expressed with these weights, because if I change this weight, the probability distribution changes. In this example, what is W? What is the matrix W? Matrix W is this weights, and we organize it this way. So the first row is these two weights. The second row is the second weight. The third row is this weight. I don't know why I wrote this, but just ignore it. And if this is a neuron J, when we say WJ, WJ is not a number. WJ is a vector that tells us what are these weights. Okay? This is useful to keep in mind, because when we go to the proof, you will maybe be confused. What are vectors? What are matrix? What are scalars? So keep in mind, this is W, and when we say W of a hidden layer, we mean a row, which is a vector. Very good. Is it standing or horizontal? By default, it is standing. If I tell you what is WJ, you should write to me. It is 5, and below it 6. By default, any row, any vector is standing unless you transpose it. In this is Boltzmann machines. What is restricted Boltzmann machines? Restricted Boltzmann machines does not have any lateral connections here to simplify things. We will see the effect of not having any weight, any connections here. And okay, this is the outcome of the proofs that we are going to see. The outcome is that the hidden units are conditionally independent on each other. So this unit does not depend on this unit, and this unit does not depend on this unit, and we will verify this by proof.